Let's talk about exponential and logarithmic equations. And, oh yeah, when we got together, the SMHS folks and I got together before the semester started, just for a little bit of review, you told me that this was one of your weaknesses. And so I gave you my college algebra notes, and I posted a link to my college algebra videos. If an hour review, actually we have 2 days for this, so if 2 hours of review is all you need to bring you up to speed on exponential and logarithmic equations, that's great. If it's not enough for you to really get the hang of exponential and logarithmic functions, then watch those college algebra videos, or those of you who aren't from SMHS and don't have those notes, if you shoot me an email, hey, will you send me your college algebra notes so I can watch those videos and take notes, I would be happy to do that. Because this is calculus early transcendental functions, we're going to hit logarithms and exponential functions very, very soon into the calculus. Actually, we start calculus, let's see, today's Wednesday. We have 2 days of 1.6, and that means Monday we'll actually start talking about some calculus instead of just algebra. And as soon as we do that, we'll be seeing a lot of logarithmic functions as well as trigonometric functions. Yay! On page 48, down toward the bottom of page 48, you have your exponential, the rules for exponents that you should be totally familiar with and bored by at this point. You know, anything to the 0 is 1. You know that when you multiply 2 expressions that have the same base, you do what with their exponents? You add them. When you raise a power to a power, you do what with the exponents? Multiply them. When you have a product to a power, you can raise each factor to the power. Don't try the same thing with a sum. You know, if you have x plus y raised to the 3rd power, for example, it's not just x cubed plus y cubed. You have to write it down 3 times and multiply it, or use binomial expansion. Enough about that. Number 5, when you divide 2 expressions with the same base, what do you do with the exponents? Subtract the bottom exponent from the top exponent. Number 6 says if you have a fraction to a power, you can raise both the numerator to the power and the denominator to the power. Number 7 says whenever you see a negative exponent, what R word pops in your head? Reciprocal. You take the reciprocal of the base. And then I added my own little number 8. I don't know why it's not there, but we talked about rational exponents. When you have a base to a fractional exponent, the denominator indicates the root you're taking. You take the nth root of the base and then raise it to the nth power. So let's do just a few problems using those exponent rules. Make sure you're comfortable with those, and then we'll talk about exponential functions. What about 64 to the 1/3? What does that mean if you wrote it as a radical? That's the cube root of 64. And the cube root of 64 is 4. How could you write b, 5 to the negative 4, with a positive exponent? 1 over 5 to the positive 4, and that's 1 over 625. Yep. What about 1/8 to the 1/3? What does that mean? Cube root of 1/8, and you may not actually need to write that middle step down. You can just squint hard and tell me the fraction you multiply times itself 3 times to give you 1/8. I'm writing down middle steps so you have it in your notes, but what is that fraction you multiply 3 times to give 1/8? 1/2. 1/2 times a half is a 1/4, times another half is an 1/8. So 1/2 to the 1/3 is 1/8 to the 1/3. Is a half. What about number 4, part C? That's just a notch up in ugliness. What do you want to do first there? And there's more than one right way to do this problem. All right, some folks take care of the negative exponents first. They write this 27 to the negative 1 as 1 over 27. Nothing wrong with that. In my opinion, that's not necessarily the easiest thing to do, because if you save the exponent, the negative exponents until the end, a lot of times they take care of themselves. So I don't worry about that to the end. I would do exactly what Glenn said. I would say when you multiply two expressions with the same base, you add the exponents. So that's 27 to the negative 1 plus 2/3 is negative 1/3. And then you still have that cube that was outside the brackets. And what would that be if I remove the brackets? 27 to the negative 1. Because when you raise a power to a power, you multiply the exponents. And then let's just make sure everybody understands the only time in math we leave negative exponents in the answer is when we're using scientific notation. If we're writing a number so small, like the mass of an electron, that we don't want to write all those zeros, we might write something times 10 to a negative exponent. Otherwise, we're never going to stop right there. 27 to the negative 1 is what? 1 over 27. All right, that's super easy. What about number, or the D part? Can I multiply and say that's 75 to the something? If you don't have the same base, you can't add the exponents. 25 to the 1/2 is what? Square root of 25, better known as 5. And 3 squared is 9.
25 to the 300.
That's oh, I haven't told y'all I'm trying to wear one contact instead of reading glasses. Y'all might need to straighten me out on that once in a while. I went to the doctor and I said, I'm tired of trying to keep glasses clean and put them on and take them off. And she said, let's try one contact. So I look like a scared horse trying to put a contact in my eye for the first time. My daughter said my eyes were just going all over the place in fear. I got it in, but it's not perfect. So yeah, tell me if I'm not reading something right. 25 to the 3/2. What does that mean to do? Square root of 25 is 5, but then I still have to deal with that numerator. That's 5 cubed. So 5 cubed times 9 is 125 times 9. And that's 900 and 200, 1125, maybe? Somebody punching it?
Did you hit record?
I'm sorry, what?
Did you hit record?
Yes. Yes. So I'll have the wild, scared horse analogy on record forever. All right, that's your properties of exponents review. Let's talk about the number E. What's the most famous irrational number in the world? Pi, 3.14157, goes on and on and on. Second most famous irrational number in the world is E, 2.71828, and it goes on and on and on. It's a little bit easier to explain where pi comes from than where E comes from. Pi, you take any circle in the whole wide world, no matter how big, how small, you divide its circumference by its diameter. It's amazing. It always turns out to be close to 3.1-ish. And that's where pi comes from. Pi is just the ratio of a circle's circumference to its diameter. E, like I said, it's a little bit harder to explain where it comes from, but I can give you one good example. If you invested $1 at 100% interest, if you found something that gave you 100% interest and you invested $1 for 1 year, how much money would be in your account at the end of the year? $2, because that's what 100% interest does. It doubles your money. And the more times your money is compounded per year, the faster it grows. So if it was compounded semi-annually, twice a year, then you would get some interest in June. And then in December, you would not only earn interest on your original dollar, but you would earn interest on that first 6 months interest you had. Now, it may not seem like a dollar is growing very fast, but if you had $1 million doing that, interest on that first half of the year's interest would add up very, very quickly. So here is the compound interest formula. A equals P times 1 plus R over N to the NT. P is the principal that you start with. P times 1 plus R, where R is your interest rate written as a decimal, divided by N. N is the number of times compounded per year, and the bigger N is, the bigger this expression grows. It's raised to the N times T. If your money is compounded, for example, quarterly, that means how many times a year? 4 times a year for, let's say, 5 years. Then that exponent would be 4 times 5. 20 would be the total number of times compounded. So if we take that compound interest formula and we let P be 1 for $1, and we let R be 1 for 100% interest, and we let N be 1, no, let's not let it N be 1. Let T be 1 for 1 year. Then when I plug all of that into the compound interest formula, I have this. And I don't know why I switched to X's instead of N's, but the more time, the bigger X is, or in the original expression, the bigger N is, the faster that expression grows. If you have a graphing calculator, I want you to graph that function. That's probably why I changed it to X's, so that you could graph it. I want to look at one plus 1 over N, or X in this case, to the X. Because we're letting T just be 1. And that's what the compound interest formula has simplified to. And I want to graph that. Just so happens the last window that I graphed something in looks like it may have gone from 0 to 10. For some reason I wasn't showing the second or third or fourth quadrant. That's only the first quadrant of that graph. But we could use trace to see what y is getting close to as our x's get bigger and bigger. I press trace and then just move the cursor to the right, and you see my x is getting bigger. 5.4, 5.5, 5.6. As my x's get bigger, I notice my y's get bigger as well. Let me change that window to what I suggested in the notes. I said, what did I say? Let's change the window to graph from 0 to 100 by tens. 0 to 100 counting by tens on the x-axis. And on the y-axis, I said from 0 to 3, counting by ones.
You have the x go on 0 then?
That's not going to work, is it? I can't count by zeros. Count by ones. All right, so I'm going to change my window so I can see more x's. Instead of just 0 to 10, I want to see 0 to 100. When I graph that again, and press trace and move my cursor to the right, again, I see my x is getting bigger. X is 52, x is 53, x is 54. But watch what's happening to those y's. Are the y's still getting bigger? Yeah, but way out there in the hundredths or thousandths or 10,000ths or 100,000ths place. They keep getting bigger. But it's changing farther and farther out there. If I made my window, if I made my x's go from 0 to 1,000, I could trace that graph all the way out to 1,000, and my y's would keep getting bigger, but they would be getting bigger farther and farther out in the decimal places. It turns out that no matter how many times per year you compound your dollar, it's never going to get quite to be $2.72. Even if you found an investment that compounded your money continuously, it would never quite get to $2.72. The bank would round it to $2.72 because we have to round to the nearest penny. That's the lowest coin we have. But it's never actually going to get to 2.72. It's going to get 2.71828 and then keep changing farther and farther out in the decimal places. So the bona fide definition of E. You've been told what E is before. Where did I just put it? Ah, there it is. The definition of E is this. And this uses calculus notation. This limit as x goes to infinity, we're going to talk about that notation next week in chapter 1. That just means as x gets bigger and bigger and bigger without bound. And if x is the number of times compounded per year, that means just compounded more and more and more and more times per year. It's never going to be quite $2.72, although that's what the bank will round it to. So I told you it's easier to explain where pi comes from than E comes from, and that's not a perfect description of where E comes from. It's just one example of the use of E in finance. So E is about 2.7-ish. Whenever I see E, I don't freak out. Pi doesn't freak me out, so E shouldn't freak me out. I just go, it's almost 3. It's not quite 3. Pi is just a little bit over 3. E is just a little bit under 3. Whatever we can do with any other number, we can do with E. So 1 over E to the negative 2. Now make sure you're paying attention to the directions here like you need to on the test. If it says give an exact answer, I don't want you to pick up your calculator for that. 1 over E to the negative 2, what would that be written with a positive exponent? The reciprocal of 1 over E is E, and taking the reciprocal of the base makes the exponent positive. What could you do in the B part? All right, you could flip it first and then take care of what's inside. That would be absolutely okay. My gut says take care of what's inside parentheses before you worry about what's outside. Not that it's going to make a difference in this problem, but in some problems it's easier to simplify what's inside before you worry about what's outside. So what does that fraction inside the parentheses simplify to? That's just e to the third. And what's e to the third to the negative 1? You could write it e to the negative 3. Or because I'm about to run out of room, you can just skip that step and write it 1 over e cubed. So anything you can do with a 3, you can do with an e. What's e to the 0? I heard somebody say 0. Anything to the 0 is 1. So e to the 0 is 1. Nothing scary about e. E is not scary.
The magical number.
No. It is magical.
Know where they come.
All right. So we've dealt with all of these exponents. We've dealt with positive exponents, negative exponents, 0 exponent. Now we've dealt with a rational exponent. The only thing we haven't talked about is variable exponents. Usually it's our base that's the variable. We deal with x squared and x cubed and x to the 10th, but x is the base. What if x was the exponent and we had 5 to the x? or we had -4 to the x, then we need to talk about that. And there's a definition right above that box on page 48. The definition of an exponential expression, f of x equals a to the x, is called the exponential function with base a. And on the line right above that, you have the restrictions on a. In an exponential function, we're not going to use bases that are negative or equal to 1. Here's why we don't use a base 1. If this was f of x equals 1 to the x, what would the graph be? All the y's would be 1. And what's the graph of y equals 1? That's just a horizontal line. If I let a be 1, then I'm just graphing a horizontal line, and that's not very interesting. The reason I'm not going to use negative bases is because my graph would bounce all over the place. When I raise a negative to an even power, I get a positive, but if I raise a negative to an odd power, I get a negative. That graph wouldn't be nice and smooth. We're going to talk about the nice smooth graph of f of x equals a to the x, where a is not equal to 1 and a can't be negative. We'll graph it in just a minute. First, let's solve a couple of exponential equations. This is an exponential equation because the variables in the exponent. One way to solve exponential equations is if you can write both sides having the same base. If you can write both sides having the same base, this turns out to be pretty easy. 1/5 to the 2x equals 625. Right now, they certainly don't have the same base, but what base do they share? What could I use as the base of both sides? They're both powers of 5. What could I put in the place of 1/5? 5 to the -1. And all I'm doing is just making this substitution, still in parentheses, still have the 2x outside. How can I write 625 as a power of 5? 5 to the 4th. You might have to do some counting on the calculator or with your fingers to figure that out. That left-hand side isn't base 5 until I remove the parentheses. That's still base 1/5. It's base 5 when I remove the parentheses and write it as 5 to the what? -2x. And then it just makes sense if 5 to the -2x is the same thing as 5 to the 4th, then -2x and 4 have to mean the same thing. So once you get both sides having the same base, you can take the bases off and just set the exponents equal to each other. Then you can finish solving for x. And that one we get x is -2. And it's checkable. If we let x be -2 in this original expression, we'd have 1/5 to the -4. The negative would flip it. There would be 5 to the +4. 5 to the +4 is 625. So if you can write both sides having the same base, exponential expression or equations are easy to solve. If you can't write both sides as having the same base, then we're going to have to talk about how to unexponentiate. I'm just going to leave that hanging because we're not going to get to it today, but we are going to have to figure out a way to solve exponential equations when we can't write both sides having the same base. One other situation that you might encounter in tonight's homework, when the base is the variable, now that's not an exponential equation really because the x is not part of the exponent. But if you want to un-4/3 something, what power could you raise both sides to? 3/4, because when you raise a power to another power, what do you do with those exponents? You multiply them, and sure enough, 4/3 times 3/4 gives you 1. So that's gonna accomplish what I want on the left-hand side. I just have to make sure whatever I do on the left-hand side, I do the same thing to the right-hand side. That left-hand side is going to simplify to just x plus 3 because 4/3 times 3/4 is just 1. What does that right-hand side mean? If you wrote it with a radical, what does that mean? 4th root of 16, which is 2, and then cubed, which is 3, or 8. I wrote 8, I said 3. And then just subtract 3 from both sides, and you have the solution x equals 5. Again, it's checkable. Just put 5 in the place of x in the original equation. 5 plus 3 is 8. 8 to the 4/3. Sure enough, 8 to the 4/3 is 16. Yes, sir. Say it one more time.
It's on this exact one, it says take plus or minus.
Let me think why the answer to that is no. And no. Oh, no, that's not the reason. Let me think for a second. Raising to the 3/4 is taking the 4th root of both sides. But if I had plus or minus 8 there, then minus 8 minus 3 would be negative 11. Negative 11 might work. Negative 11 plus 3 is negative 8. I can take the cube root of negative 8 is negative 2. Negative 2 to the 4th power is 16. So you were sharp as a tack to realize that. And I need to make myself a note out here. Raising something to the 3/4 power is taking an even root. And whenever you take, y'all are laughing at me, aren't you?
I mean, a little bit.
Because I've already typed it. I'm writing it and I've already typed it right there.
Oh, yeah.
That may or may not be what he said we did.
Whew. I'm doing good. I'm doing good to be here. Yeah, whenever you take an even root, don't forget the plus or minus. So I not only get the 5, but I get the negative 8 minus 3 is negative 11. So thanks for pointing out what I already typed, but forgot to read. All right, let's keep going. Anytime we graph something for the first time, we have no idea what shape it's going to be. What's our fallback method for graphing? Make a table. When in doubt, when you don't know what else to do, make a table. Actually, I might have to come back to that basic graph. Let me make a table for number 26. I'm gonna eeny, meeny, miny, mo, but not really, and I'll tell you why in a minute. Eeny, meeny, miny, mo, I'm gonna let x be -1, 0, 1, and 2. I might have to pick some more x's, but let's start with those. If I let x be -1, this is 3 to the -2. What's 3 to the -2? 1 9. If I let x be 0, this is 3 to the -1. What's 3 to the -1? 1/3. If I let x be 1, that's 3 to the 0. What's 3 to the 0? 1. And if I let x be 2, that's 3 to the 1st, which is 3. Graph those 4 ordered pairs. 0, -1, or -1, 1/9 is just barely above the x-axis, so close I probably couldn't even spot it on the graph. 0 1/3, maybe right here. 1 1, 2 3 would be up there somewhere. What's going to happen as my x's get bigger and bigger? What do you think's happening to my y's if I let x be 3, then 4, then 5? They're getting big fast. Powers of 3, 3, 9, 27, 81, 243, they get big fast. So the right side of that graph is taking off very steeply. What about as x's get infinitely small? 3 to the negative 3, 3 to the negative 4, 3 to the negative 5. Closer and closer to 0, am I ever going to get a negative answer? You can't raise 3 to a power and get a negative answer. Can you get 0? No, if you raise 3 to the 0, you get 1. And you can get close and closer and closer to 0, but you're never going to hit y equals 0. So this graph gets closer and closer to the x-axis. What do you call the horizontal line that a graph gets closer and closer to as x goes to either positive infinity or negative infinity? It's an asymptote. That's the basic shape of the graph of any exponential function with a base bigger than 1. And we'll talk about when the base is not bigger than 1 in a minute. But the things that you just need to know about any exponential function in the whole wide world. The critical point is 0, 1, because regardless of what the base is, the base is 5, I have 5 to the 0, that's 1. If the base is 10, I have 10 to the 0, that's 1. 0, 1 is called the critical point, really for 2 reasons. Number 1, every exponential function in the whole wide world, regardless of base, if the graph hasn't been shifted left, right, up, or down, it's going to go through the point 0, 1. That's one reason I'm calling it a critical point. The other reason I'm calling it a critical point is that's where the curvature really changes. This graph was growing pretty slowly up until it hit that critical point. Once it hit that critical point, it took off very fast. That's exponential growth. When you say something is growing exponentially, the mice in your kitchen, heaven forbid, if they start growing exponentially, one day you have 2 mice, the next day you have 8, and then 16, and then 32, and then you just move. You're not winning that battle. Unfortunately, the national debt's growing exponentially. We have way surpassed that critical point. I'm sorry, people, your future is bleak.
Yeah, we know.
You've been told that before. Because the national debt is increasing exponentially. There's almost no way, short of, let's not even go there. There's almost no way that we're ever going to pay off the national debt. I didn't mean to take you to that dark, dark place. But the critical point, 0, 1, the horizontal asymptote is y equals 0, unless the graph has been shifted up or down. And then the same things that shift parabolas, left, right, up or down, or flip them upside down, those very same things shift the exponential function, left, right, up or down, or flip it upside down. This one that we graphed by making a table, if I had known what the basic shape of any exponential function looks like, I could say, well, this one's going to look just like it, except for, remind me this real quickly. If I'm graphing y equals x squared, but then I subtract 3, subtract 3 before I do the squaring, how does that affect the graph? Shifts it to the right 3. This is just the same graph as this, shifted to the right 1. because 1 is subtracted from the x before you do the exponentiation. So the critical point, when I'm graphing an exponential function, I say normally the critical point is 0, 1, but if I shift that to the right 1, if I start at 0, 1 and shift it to the right 1, where's that critical point going to be? 1, 1. And that's exactly what we found out when we made a table. That critical point was 1, 1. The horizontal asymptote was still y equals 0 because this graph wasn't shifted up or down. What would shift the graph up or down? What would shift this parabola up or down? If I added or subtracted something after I did the squaring, if I put a plus 2 on the end, that parabola would be shifted to the right 3 and up 2. I don't have an example specifically of that here, but if there was a plus 2 on the end of this exponential function, then the horizontal asymptote would be shifted up 2 as well. Whenever you have a horizontal asymptote, make sure that you dot it in, put a dash line for your horizontal asymptote, because I know that you know that it's there. When you graph something with a horizontal asymptote on the calculator, just another example of why you have to be smarter than your calculator. Give me an example of an exponential function that would have something other than the x-axis as its asymptote.
Y equals 2 to the x power.
2 to the x power, gotcha.
And then the entire thing plus 2.
Plus 2. And I don't have to use parentheses there because the calculator automatically does exponents before addition. So let me set this back to a standard window. That particular one didn't do what I was going to caution you about, but sometimes when I graph exponential functions on the calculator, it looks like they just stop right here because it can't show getting closer and closer, getting infinitely close to that horizontal asymptote. So you have to be smarter than your calculator. If your calculator looks like it stops right there, you say x can get smaller than that. X can get infinitely small, but y is never going to drop down below 2. If I wanted to flip this parabola upside down, how would I accomplish that? A negative exponent, or not a negative exponent, a negative coefficient. Negative x squared would be an upside down parabola. This is going to be an upside down exponential function. But look at that exponent. X over 2. What's another way to write x over 2? It's the same thing as 1/2 x. That 1/2 is going to change how quickly the graph gets big, but unless you're doing it on graph paper, you're not going to be able to tell. If you graphed e to the x and e to the 1/2 x right on top of each other, e to the 1/2 x is going to get big a little more slowly than e to the x, but unless you have them right on top of each other, you're not going to be able to tell. If I'm just trying to get a quick mental image of what this graph is going to look like, so that if my calculator gives me something crazy, I'll say, hey, that's crazy. I must have made a typo. We're just going for a quick mental image, then that'll be good enough. Just take that normal exponential function and flip it with respect to the x-axis. All right. Let's talk just a little bit more, and then I'll tell you where to stop in the homework. Every time we've learned to do something, we've learned to undo it. We learn to unadd, called it subtract. Learn to unmultiply, called it divide. We learn to unsquare, called it taking the square root. It's time to learn to unexponentiate. Logarithms are what we use to unexponentiate. Now let me just kind of make an aside here. Make sure you understand what logarithmic notation means. If I say log base 2 of 16 equals blank, then what I'm really asking you for is the exponent. I'm looking for the exponent of 2 that gives you 16. So you just count on your fingers to see how many times you have to multiply 2 by itself to get 16, and it's 4. You can check that by raising 2 to the 4th power and make sure it gives you 16. This is exponential form. This is logarithmic form. Exponential form and logarithmic form are just two ways of writing the same thing. Just like most fractions can be written as decimals, or decimals can be written as fractions, and you're not frightened of that. They're just two different ways of writing the same thing. The same applies to exponential and logarithmic form. So what if I said log base 2 of 1/8? What would that be? You're squinting real hard and thinking, what exponent of 2 could give me 1/8? Well, the only way an exponent of 2 is going to give me something smaller than 2 is if it's negative. And then what power of 2 would give me 8? 3. So log base 2 of 1/8 is -3 because 2 to the -3 gives you 1/8. 2 more. What about log base 2 of 1? 0 is the exponent of anything that gives you 1, no matter what the base is. Log base 2, log base 10, log base 44 of 1 is 0 because anything to the 0 gives you 1. Last one. I heard 1. If it is 1, I should be able to check it. How would that check work? 2 to the 1st would have to give me 0. Is that true? That's not true, so that can't be true. Squint harder and tell me what exponent of 2 would give you 0. I don't think I'm going to be able to come up with that no matter how hard I squint. There is no power of 2 that's going to give me 0. This is the second thing we've encountered in math that we're going to call undefined. What's the first thing in math we call undefined? Dividing by 0. If we have 0 in the denominator of a fraction, we write undefined. If we have log base something of 0, we write undefined. So what if I said log base e of e to the 4th? What's the power of e that would give me e to the 4th? Because log base e of e undo each other. There's an abbreviation for log base e, and that abbreviation is what? Natural log is just the abbreviation for log base e. So back to the handout. for all x's greater than 0, natural log of x equals b means that e to the b gives you x. That natural log of x is just an abbreviation for log base e of x. So if I give you something in natural log form, you should be able to change it to exponential form and vice versa. I just wrote something I've already typed again. Natural log of x is an abbreviation for log base e of x. So number 58 says, write the exponential equation as a logarithmic equation. Just going back and forth, just like we did here with other bases, let's do it with base e. When I see e to the negative 2 equals 0.1353, I could change it to a logarithm. It would be log base what? Same thing the base is over here. Log base e of what? The 0.1353 equals what? It's always the exponent that's on a side by itself, but you're never going to see log base e in any self-respecting math book, because what's the abbreviation for log base e? That's just natural log of 0.1353 equals negative 2. Or number 60, if you give me something in natural log form and I want to change it to exponential form, what base do I use? E, and e to the what? The negative 0.6931. Whatever's on a side by itself, that's the exponent. E to the negative 0.6931 equals what? The 0.5. All right. Let's do these. Let's not. I don't think we'd have time to finish them. So let's just say we're going to stop right there. And in the homework, I think that means you should be able to go through number 59. Let me double check that. 59, yes, that's a good place to stop. So that's tonight's homework. See ya.